feature importance, explaining uncertainty estimates, will be presented by Javier. He is also a PhD student at the University of Cambridge. His research interests include Bayesian deep learning, uncertainty in machine learning, very fitting, and representation learning, as well as information theory. And today, Javier will be presenting some of his most recent research work, which has been influenced by the findings of the work that Oman is going to talk about. So it's two very connected talks, and specifically Javier will talk about ways to incorporate uncertainty into explainability. He'll present a new method and talk about how this method compares to existing explainability techniques. Like I mentioned a little bit earlier, Javier is calling all the way from Europe. He's very generous with being available in this really late hour, so please be extra welcoming, extra excited, and extra engaged for his talk.
Cool. So I'm Javier Antorán. I'm a PhD student at Cambridge, and I work on interpretability, probabilistic model, representation learning, and my talk is titled Beyond Feature Importance. So the promise of interpretable machine learning is that we would be able to deploy a very complex system without sacrificing interpretability. So we would also be able to understand why our system does what it does, why it makes decisions. And if it hasn't become abundantly clear from Umang's talk, we're still working on this problem. It's kind of hard. But in this talk, I'm going to focus on some situations where existing techniques, namely feature importance, break down, specifically when there is model uncertainty in play. So an alternative title for this talk, which I couldn't really decide on, would be Recent Trends in Machine Learning Research and What They Mean for Interpretability. And the outline is going to look something like this. I'm going to very briefly review what approaches are most popular for interpretability. I'm going to introduce counterfactual approaches, which are ones that Umang briefly touched on and I have a specific preference for. Then I'm going to give a brief overview of uncertainty in machine learning, which is quite a hot and trendy topic at the moment, I think. And then we're going to look at the intersection of interpretability and machine learning. Specifically, we're going to focus on some recent work in collaboration with some people at Cambridge, including Umang, called Clue, which aims to give explanations for situations into which our models are uncertain. And finally, I'll take some questions. So there exists many interpretable data-driven decision-making models, like linear regression or decision trees. So just to give a very brief recap, linear regression gives an output, which is a weighed sum of each input feature, x1, x2, x3, etc. And the weights, W1, W2, W3, act as the explanation. If a feature is very important, then its weight will be a very large magnitude. And if a feature contributes to a positive classification, its weight will be positive. If a feature contributes to a negative classification, its weight will be negative. So once we have fit a linear regression model, figuring out the reasoning of the model is pretty trivial. The case is very similar for a decision tree, where the model simply consists of a series of binary yes/no questions, which could look something like, is feature x1 greater or lesser than 3? And once we've asked all of our questions, we sort of categorize the input into a leaf node for which the predictions are constant within the leaf node. So then we get a function that looks somewhat like the bottom right, where it's piecewise constant. However, if we sacrifice interpretability, we have access to a much wider range of predictive models, like neural networks, for example. And these can do really cool things, like take the image of a road and output the driving commands that would be optimal for a car. Although this image on the right is kind of a joke. I would not fall asleep on the wheel, even if you do have a self-driving car. So to be more concrete about what we gain if we sacrifice interpretability, we gain the universal approximation theorem, which basically says that our neural networks can capture any function in existence if our neural networks are large enough. And we gain scaling to very high dimensional problems, which the previously mentioned interpretable methods cannot do. Cool. So once we've sacrificed interpretability and are using a neural network, we can try to think, how do we get it back? So the most commonly used approach in practice is feature importance. And probably the most well-used approach within the family of feature importance techniques is LIME, which stands for, actually can't remember what it stands for, but some linear surrogates or something along those lines. So the idea behind LIME is that you approximate your nonlinear model with a linear function, which is interpretable. So say that our predictor is a neural network, F and N. We can define an approximate predictor, which is just a linear regression model. And we can try to get this linear regression model to approximate the neural network's prediction in a specific region. Yeah, thanks. Somebody put it in the chat. It's local interpretable model agnostic explanations. So, and yeah, there's a GitHub repo which you can download and run everything from. It's quite easy. So you approximate your neural network with the linear explanation in a specific region, which is what I depict in the bottom left picture. So here, the true function is quite curvy. It's kind of circle shaped and closes in on itself. And the linear approximation is only going to be true very locally around the gray star. And it's going to be more true for x1 than for x0, because large changes or even moderate changes in x0 will cause our true neural network function to sort of change direction. And then our linear approximation will almost be the opposite of the truth for this model. So we could argue a lot about the reliability of this sort of approach. But before that, let's look at some examples for images. Images are much more high dimensional. So this linear plane that we're fitting becomes a lot more. So to put this in an easy to understand way for high dimensions, so it's very unintuitive when you think of high dimensions, but if you take a linear approximation in a high dimensional space, the variability in this approximation will be much higher, and often what you'll get will be much less meaningful. And this is really easy to see in practice. So if you take this example of a handwritten digit 2, which we're trying to classify based on the image as one of the 10 digits that exist, the positive evidence that LIME finds for class 2 is the complete digit 2, which it seems very reasonable. The positive evidence it finds for the second most probable class 3 is the kind of this rotated U shape near the top of the 2, which could be the top of the 3. So this also seems reasonable. But then if we look at the third most probable class, which is 1, we find that LIME thinks that all of the pixels of these image contribute positively to the classification of 1. This is happening because in the local region around this point, all of those pixels do indeed give evidence for the class 1, but they give much weaker evidence than for class 2. And this is something that it's very difficult for LIME to express. So in this scenario, which is not that high dimensional compared to machine learning and deployment, we're already seeing failure modes of LIME. So the alternative to feature importance explanations are counterfactual explanations. So counterfactuals capture the notion of how things would have worked out if some factor would have been different. So counterfactuals are very relevant to scenarios like medical diagnosis, where we make some intervention, observe an outcome, and then based on this information that we've learned, we would like to answer questions like, what would have been the outcome had we not made the intervention, or had we made some different intervention? And using the term somewhat loosely, the interpretability community has started using counterfactuals to ask questions of the sort, what intervention would I need to make in order to get a desirable outcome? If we want to explain a classifier, the question we could pose would be something like, what features would I need to remove such that my model's confidence decreases? Or what features would I need to change such that my model makes a different classification? And the cool thing about counterfactuals is that they're completely model agnostic, and that their explanation has a very solid meaning without any approximations being in the way. So before, when we were using this linear explanation to approximate a very high dimensional a very high dimensional predictive model, then it's not clear how much of the explanation that we're seeing is coming from the approximation and how much is actually the model. Well, in the counterfactual case, we have the guarantee that it's completely the model that's generating the explanation for us. So to make this more solid, I have an example from a very interesting paper from Cheng et al., where they generate counterfactual explanations for image classifiers. So if you take this image of a bird, which is on the left-hand side, and you ask a question of the sort, what pixels would I need to remove in order for this to no longer be confidently classified as a bird, we can see that their method successfully removes all the bird pixels and substitutes them with a background. And this is really cool because now it allows us to generate these heat masks of pixels that are especially relevant for prediction. Yeah, thanks, Alicia. She put the paper in the chat in case anybody's interested. They also have public code. And now now that we've introduced counterfactuals, doing a quick topic switch, let's give a quick review of uncertainty in machine learning. So despite neural networks having gained a lot of popularity recently, a well-known issue is that neural networks are very overconfident and tend to behave erratically in scenarios that are different from the ones that they've been trained on. And not only do they behave erratically, but they often have very high confidence in their erratic behavior. So this is illustrated by this cat being classified as a dog with nearly a probability of 1. So let's look at why this bad behavior is happening. So there's 2 reasons why your model should be uncertain. The first one is that there's noise in your data. So we're going to look at this example of the moons data set, which is sort of 2 half moons interlocked with each other. And we're going to consider a scenario where we have a linear classifier, so just a logistic regressor. Since we would need a nonlinear decision boundary to separate these 2 clusters, our model thinks that this is an impossible task. It thinks that there's inherent class overlap in the data, that there's noise. And this is reflected in noise uncertainty, which I've sort of depicted the areas of high noise uncertainty in the middle plot. And it's just the region of class overlap. We also refer to this as aleatoric uncertainty. The other reason why your model would not know what the correct class is because you're querying it about points that are very different than the ones it's been trained on. And then it expresses what we refer to as epistemic uncertainty, which another way you can think about this is that you're querying your model, you're asking your model a question about which its parameters have not been adequately constrained to answer. And we see this in the right-hand side plot, where there's really high model uncertainty in all the regions that are far away from the training data. So let's give a more intuitive example of what this means. Imagine that we have a coin. We want to predict a coin toss. We want to see if it's going to be heads or tails. And to do this, all that we have is data from previous coin tosses. And also there's a catch. The coin might not be unbiased. Perhaps the probability of heads is not 0.5. We don't know what it's going to be. So if we observe 2 coin tosses and they both come up heads, the maximum likelihood solution, the naive approach, would say something like, well, we've only seen heads, so then the probability of heads must be 1. But intuitively, this seems like a very bad idea to make this decision. A more sensible approach would be to say, I choose the continuous red line in this plot here, and I assign more probability to heads than to everything else, but I don't discard all the possibilities that are not P of heads being 1. If we observe 50 tosses and we get 10 heads and 40 tails, then we could be a lot more confident that the probability of our coin coming up as heads is 0.2, but still it's reasonable to have confidence intervals. Maybe due to variability in the tosses, the true probability is 0.15, maybe it's 0.25. And we can take the same concept and apply it to probabilistic models like neural networks. So here, what we want to estimate is not the probability of a coin coming up as heads, but it's the probability, our network weight value should be, so what our parameters should be. So just like before, where it might not be very sensible to choose a specific value, but we would like to encode our uncertainty through a probability distribution, the same can be said about our neural network parameters. So it's a well-known fact that a neural network optimization landscape is very non-convex and quite funky, like the one I've depicted here. And it's also pretty well studied that if you optimize this objective with different initializations, you might converge to different solutions. And all of these solutions might be equally good, as shown by my 3 stars that I put on this plot. And in the bottom 3 plots, I show how each of these stars corresponds to a different function, which have the same color as the stars. And all 3 functions are very good. They all perfectly pass through all the training points. But where they differ is in the region where there is no data. They disagree with each other. And this disagreement among the different functions is what we know as model uncertainty. And it's an expression that in those regions where there is no training data observed, we really don't know what the function that our network expresses should be. So in summary, what we're doing here is we're saying we substitute the weight values of our neural network with probability distributions that are going to allow us to capture model uncertainty. Because I might have forgotten to mention this, but a regular neural network or a regular predictive model that's most commonly deployed can only capture noise uncertainty. It doesn't know anything about model uncertainty, so it's completely incapable of knowing if it's faced with an unseen or a very strange input. It doesn't know when it doesn't know. So in practice, doing this Bayesian neural network thing is pretty tricky because the loss landscape of the neural network is quite complicated, as shown on the right. And we often just use very crude approximations, like the one I depicted on the left in this red curve. Of course, the red curve is not very representative of the complete loss landscape, but it's the best we can do. And the reason why I mention this is because we shouldn't take machine learning uncertainty estimates as the ground truth. In practice, very often we will not be able to completely characterize all of the functions that our model could express, and thus we will be, our uncertainty estimates will be biased. So we need to keep this in mind. Very often we're going to be underestimating uncertainty, but that's better than completely ignoring it. So cool, just one final note. In order to quantify uncertainty, if we would like to get a number which expresses if we're uncertain or not, we often do the following. For classification, we can just use entropy. So a very spiked distribution where only one class has all the probability mass would be very low entropy. And a very flat distribution where all the classes are equally probable would be very high entropy. And for regression, we can just use predictive variance, which amounts to saying how big are the error bars. Cool. So why would we use uncertainty in practice? So the most obvious reason is robustness. We wouldn't want our self-driving cars or our medical diagnosis systems to act erratically when they're faced with something very different from their training data. And a good way to implement this is to have a reject option. So if your medical diagnosis system decides that it's seeing something that's very new to it and it doesn't know what to predict, it could simply reject to make a prediction, and then we could query a human expert about the input. Another reason is data set building, safety and fairness. So suppose we're trying to build a data set to do some fairness sensitive task like hiring. So it's very likely that because of demographic disparity, different subgroups would be differently represented in our training data. And this would probably bias our model's predictions. However, if we have an uncertainty-aware model, we'd be able to identify that we have very high model uncertainty for subgroups underrepresented in the data, and we could use this sort of as an alert, as an alarm, which could tell us to, look, you need to collect more data about the subgroup in order for your model to be making fair predictions. The final use case for uncertainty is active learning, which is the scenario in which you don't have many labels and getting them is really expensive. So think of a scenario where in order to get labels, you have to query a human expert, like a doctor. So here, what we would like to do is identify which points would be most useful for our model to get the labels for. And it turns out that those points are the points of high model uncertainty, which are the ones depicted here with the star and the vertical line. And before moving on, if you want to play around with these ideas and you want to implement Bayesian neural networks for your own, you can use our public code, which is actually now in the chat. Cool. So let's get back on topic. Are uncertainty-aware systems interpretable? So thankfully, they're as interpretable or not interpretable as regular models. So if you're using linear regression or probabilistic linear regression, then that will be quite interpretable. But if you're using a Bayesian neural network, like the ones in the repo linked, then it will probably not be very interpretable. However, there are some hidden perks that come with uncertainty. And we can look at them with this polyp segmentation example that I place here at the bottom of the slide. So the objective of this neural network is to segment the region where polyps appear in the image. And it does it quite well. And then, as shown in the second plot. And in the third and fourth plot, we show the uncertainty estimates given by this model and a linear feature importance explanation. And the uncertainty estimates look like that because they sort of look like the regions of the polyp, because the network has been successful in identifying the polyp, but it doesn't really, it's not really sure about where it starts and where it ends. And that's reflected in the uncertainty. And this ends up being quite a better explanation than the feature importance explanation. And we sort of get this for free once our model expresses uncertainty. Just quickly before moving on, a question in the chat is, what are your suggested resources to getting caught up on the uncertainty in machine learning space, survey papers, introductory textbooks? Right. So I think the survey that Umang sent is quite good. I'm familiar with that one. Often I feel like probabilistic machine learning can be a bit of an entry barrier, because people sort of use their own language, and once you know what things mean, it's quite simple. It's not hard at all, but at least for me, it wasn't. I had to sort of spend a couple months going at it, and I'm trying to think what were the best resources for me. There's a course on Coursera by the Higher School of Economics in Moscow, Russia, which I believe is called Bayesian machine learning or probabilistic machine learning, something along those lines. And it covers a very wide range of things, and it has introductory parts and also advanced parts. But even if you don't understand anything, it will get you used to the language and the concepts. And I think that's a very solid stepping stone to taking a deep dive into a probabilistic machine learning. Cool. So back to interpretability. What happens when our model doesn't know the answer to a question? Because we've already seen that if our model is confident about a prediction, yes, that is exactly it, the one that's in the chat. Thanks. So right, so if our model is confident, we can always use LIME, SHAP, or one of the many feature importance methods or counterfactual methods that exist, like Ph.D, for example, is the counterfactual method that I showed earlier. But what happens if our model triggers the reject option? What happens if it doesn't know what to predict? So let's think of what would happen if we use a feature importance method. The feature importance method essentially tries to highlight the evidence for each class. But what if there's conflicting evidence? So various classes have high evidence. Or what if there's a complete lack of evidence because we have model uncertainty? So this suggests that maybe using a feature importance isn't the most sensible thing. But then this gets compounded by the fact that uncertainty estimates are nonlinear, even for the simplest of predictive models. So consider the probabilistic linear regression example for before. Even though the decision boundary is completely linear, the uncertainty estimates shown in the middle and right-hand side plots are very curvy. They're nonlinear. So even if for the simple model, if we were to apply LIME, we would be doing quite a crude approximation. However, none of this is true for counterfactuals. But before we jump into counterfactuals, we have to address one last issue. So suppose that we were to pose the problem as, let's find an image that's similar to our original image, but for which uncertainty is no longer so high. So if we naively try to optimize for this, we might find something like an adversarial example. Just a quick recap, an adversarial example, an adversarial attack is the idea that you could take a correctly classified image, like this panda, add an imperceptible amount of noise, but a specifically crafted noise for this attack, and end up with your model predicting an arbitrary class, which is not the correct one, with very high confidence, which is what happens here. And the same could happen for uncertainty, where you could have an image of a digit that's a little bit pixelated, it's missing the top part of the 8, as shown in the bottom plot. And we could take a step in the direction of the entropy, a gradient step, and end up with a completely, with the same image with just some noise added, but with a much lower entropy. So the first image had entropy of 1.77, and the second has entropy of 0.12. And the only thing that's happened here is that we sort of tricked our network into thinking that it's confident, but we haven't really learned anything about our data. Instead, we could take a cue from the drug discovery literature, where they have this problem that they want to find new drugs to cure diseases, but creating synthesizable drugs is really difficult. If you sort of make a random compound, the most likely thing is that you can't actually build that drug. So they try to model all the possible drugs that could exist using a generative model, and then restrict their research space or their hypothesis space to that generative model. And if we apply this to generation of counterfactuals, we'll end up with something that's similar to what I show in the bottom plot, where we map our uncertain image to a latent space, to a restricted hypothesis space, make the search in this restricted hypothesis space, and map it out to a certain digit, which is actually relevant, which actually represents an answer to our question. Which in this case, it turns out that in order for your model to be confident, you sort of need to unpixelate the image, fix the bottom part, and maybe add sort of a hint of a closing line on the top. So this is exactly what our recently developed method does, which we call CLUE, which stands for Counterfactual Latent Uncertainty Explanations. And CLUE answers the question, what's the smallest change you need to make to an input while staying in distribution, which means while staying relevant, such so that our model produces more certain predictions. So now we can plug CLUE into this pipeline, and the second that you input some uncertain input, like this image of a 6, which could be a 6 or it could be an 8, because there seems to be an extraneous line, we can trigger the reject option. We cannot make a certain prediction, and then we run CLUE, which gives us the nearest certain image, which turns out to be a 6 with that line removed, and specifically highlights what the issue was. Gives us the saliency of the pixels we need to remove. So doing this is actually pretty simple. We define an objective, which we call L here, which is simply we want to minimize the entropy of the prediction, and we want to also minimize D of the explanation and the input, which is a distance between the explanation and the original input. We simply take this distance to be L1. And we perform iterative optimization, where we take a point in latent space, which is a point from within our generative model. We generate an input from this point in latent space, and then we evaluate the uncertainty of this input. Then we simply take the gradient of the uncertainty with respect to latent space and move in the latent space. The latent space, you could think of a constrained hypothesis space, where all the points in the latent space map to relevant points in input space. In this way, we ensure that we don't generate noisy or inputs or adversarial examples. So let's look at what this does in practice. So defining this delta x as the difference between the CLUE and the original CLUE, we see that when we give CLUE some funky uncertain inputs, it sort of tells us what went wrong and what we would have to change in order for our model to not be uncertain. In the case of handwritten digits, it's really intuitive how we go from extra lines to sort of more canonical versions of those digits. But we can apply this technique to classification, regression, tabular data, and image data. And we show that with the second example, which is from LSAT, which is a data set where the objective is to predict academic performance. And we see that for the original input on the left, our model was quite uncertain. And it turns out that making these changes to the to a candidate's undergraduate GPA and race, our model would be more certain. And this can open up questions about, this can perhaps give us some insight or make us ask some questions about how our model is reasoning about these different features and if we should make some changes. So we'll get more into this in the following slides. But before that, let's quickly compare what CLUE does to what feature importance methods would have done. And a key idea that I've yet to introduce is that because CLUE is counterfactual, it can add new information that didn't exist before in the input. But feature importance methods simply limit themselves to highlighting the different features if they provide evidence for a class or if they provide evidence against a class. They're incapable of adding new information. So if we take this top row where we have a 6 that seems to have an incomplete stem, CLUE directly sort of says, look, you should just fill in these pixels and then I would be very confident. However, when we sort of ask Lime or Shap for the evidence in favor of different classes, we get something that's sort of meaningless because it's impossible for these methods to give us the correct answer. It's impossible for them to add features. We see the same effect in the middle row. The bottom row, I think, is especially interesting because it's kind of a specific scenario where feature importance can go right. Here, what happens is that we just have some extra pixels. This 7 perhaps has an extra long stem going down on the left. And it turns out that if we sort of trimmed it, our model would be more confident, as shown by Clue. And when we apply feature importance, things actually go right, very luckily. And if we look at the evidence for and against class 7, this extra stem is highlighted by both Lime and SHAP, which are two feature importance methods, as evidence against class 7. So I guess in some cases, feature importance could work, but this is kind of a one-off that I put in here to show the example. It's very rarely does this happen, especially with more complex data. Cool. The final thing I'm going to talk about is a user study, which we use to validate if this idea of explaining uncertainty estimates is something that's useful at all. Because this is quite a new concept, and it wasn't clear to us if this would be intuitive to practitioners, or if this could actually lead to actionable conclusions. So we propose a human simulability task. And the idea is that an explanation should give a user enough insight to be able to predict how a model is going to behave in a new unseen circumstance. So specifically what we do is we present some users with some context examples, which are an uncertain and a certain point, labeled as such. And based on these, we want them to predict if their model will be confident or not confident on a new previously unseen test point. And the idea is that based on the context points, our users should learn about the potential failure modes of our model, or the regions where our model has not been properly trained, so they can identify if that will be the case for unseen points. How we set this up. We use two data sets, COMPAS and LSAT. The first one is predicting criminal recidivism, and the second one is predicting academic performance. And we take users from Cambridge University undergrads that have taken at least one machine learning course. And we run 4 approaches. So we run Clue and 3 competing approaches that act as baselines. And we assign 10 users to each baseline and Clue. So we build the test as follows. First, we run a pilot procedure where we have an additional user, which will not take the test, and we have him select a series of test points, which we will query our users about. This participant also selects a set of uncertain points, which he deems to, or she deems to be relevant to the test points they've selected. In this way, we ensure that the uncertain context points are relevant to the test points. We then use the methods under consideration to generate counterfactuals. So to generate certain points which are supposedly related to the uncertain points and explain away their uncertainty. To do this, we use Clue. We use sensitivity, which is a method, it's a very basic method. It's similar to Clue, but it doesn't restrict the hypothesis space to relevant points. So it could, in principle, generate anything. It's a little bit more flexible. We also use another baseline is human Clue, which is a fancy way that we use to call our test point selection participant also selecting the certain points. So it's sort of asking the person that's selecting the points to find certain points that are also relevant, to sort of manually select a counterfactual. And then as our final baseline, we include random selection, which sort of is there to check if our method is doing anything at all. So the results that we get are shown on this slide. So we get very similar accuracy, interestingly, for human Clue, where the human participant selects the certain examples, and for random selection, making me think that probably human intuition is not very good if it doesn't really do any better than random. And sensitivity does especially bad, which sort of tells us that if you don't constrain your hypothesis space to relevant things, you will generate adversarial explanations, and these will confuse you more likely than help you. And Clue does the best, And not only does it do best in terms of average accuracy, it's the only one that's statistically significant over all the other approaches. And the other approaches are not statistically significant with respect to each other. So I think a conclusion that I draw from this is that one, human intuition is not necessarily very good for explaining uncertainty, and two, that a data-driven method that takes into account the model being explained, like CLUE, because the model being explained as part of a CLUE pipeline, is a lot stronger. Cool. We run a very brief separate analysis with images, where we craft a special MNIST data set where we take all the sevens, we remove the horizontal dash stems, we remove the sevens with the horizontal stems cutting them, and we remove the fours with a closed triangle-shaped top. So then we induce model uncertainty for when our network sees these type of digits, and no uncertainty for the other digits because they're present in the data set. And we run a very similar experiment, except now as a baseline, we have both CLUE and we have just what we call uncertainty, which stands for just showing users the label of this is a certain or uncertain image, but we don't tell them what they should change in order to reduce uncertainty. So essentially what we're checking for here is if with a very intuitive type of data, like these digits, which you can analyze visually very simply, if it's really necessary to give an explanation, or are just labels good enough. So based on having seen 10 images with labels of certain or uncertain, could you just simply infer if, could you simply infer the failure modes of your model? And oops, didn't mean to do that. So my chat window is right on top of my results, so I really can't see how well CLUE does compared to the baseline, but I recall that CLUE did quite a bit better. I think it was 80 something to 60 something. At any rate, I don't think it matters too much what the specific value is. But the conclusion is that it seems that despite the type of data we're looking at being quite intuitive, that still having the specific explanation of what went wrong or what is the failure mode does help users. Cool. So this work was done in collaboration with Umang, with Tamim, Adrian Weller, and Jose Miguel Hernández Lobato at Cambridge University. And I would like to give them a big thanks. And now I'm really happy to take questions. If you want to read the full paper, it's at that link. If you want to see more related research for both general probabilistic modeling and uncertainty and deep learning, you can go to my website. And if you want to contact me about anything, that is my email.
Incredible. Thank you, Javier. This was, in addition to the uncertainty and CLUE, a really, really great walkthrough of explainability techniques.
Cool, thanks.
So anybody wants to jump in with questions? I'll give people a few seconds to gather their thoughts. Really? Okay, well, while y'all are thinking, I have a question. Okay. So in the first talk, one of the dimensions of explainability that Umang mentioned that is certainly not working out too well for deployed systems is performance and computational complexity. Can you talk a little bit about how CLUE compares in performance to other popular explainability techniques, and what gives it an advantage versus others?
Sure. So in terms of computational cost, I think it makes more sense to, instead of making the distinction uncertainty explanation versus non-uncertainty, it makes more sense to do counterfactual versus non-counterfactual. I think that a counterfactual explanation is inherently not untrue, like feature importance explanation. So they have a very large advantage in that they don't make any approximation, but the cost is compute. So, so that's pretty, so in that sense, that's a pretty relevant question that I did not touch on. So CLUE does iterative optimization. and although that's also true for something like Lime, in practice, Clue has to do. No, actually, what I was going to say that Clue has to do multiple network evaluations, which is true, but Lime also does that. So I'm trying to think of. So I was very convinced as soon as you asked the question that counterfactual methods were more expensive because they all rely on optimization. And this is not very good because you need to evaluate multiple times your network. Yes. But actually both SHAP and Lime also do that. Yep. So perhaps counterfactual explanations are not more expensive.
You need a VAE, right? Right. Like
sorry?
The complexity also comes from the VAE, like how good your generative model is. So
right, but that's linear. I mean, sure.
Yeah, I mean,
Umang is right. Sure. So I think that very generally, probably there is no difference in terms of counterfactual versus feature importance explanation. Clue has the added expense of having two models because you have a generative model and a predictive model. So you have to also evaluate the generative model. Generally, people would not. I think that if you wrote this down in a paper, you would not say that it's more expensive because it's a linear cost. So you would still write that as O of n. But it's true that it's double potentially. This is also true for the other counterfactual method, which I sort of glossed over, Ph.D, which does counterfactual explanations for images. It also uses a generative model to constrain the explanation space. So perhaps the additional cost that you could have is that if you're using some sort of other neural network to constrain your hypothesis space, evaluating it will incur a cost.
Makes sense.
Yes, maybe that was a bit more rambly than I would have liked.
That actually provided a ton of detail. You really broke down the runtime there. Cool, thank you. There are a few people with questions.
Any uncertainty study on object detection topics? Uncertainty. Oh, what exactly do you mean by? As in, like, applying probabilistic methods to object detection, like segmentation tasks, for example, or the bounding box tasks. Cool. Yeah. So I think that the most relevant work to that is by Alex Kendall and Yaron Gall, and it's titled "What Uncertainties Do We Need for Computer Vision?" It's but the general idea is that all of these probabilistic methods sort of scale to all types of neural networks, but the approximations can be arbitrarily bad. And if you use a very small neural network, then your approximation is less bad than if you use a very large, complex, convolutional neural network for object detection. So you have to be really careful when you're using these really big models if you're trying to do probabilistic inference, because your approximation to the posterior distribution over the weights might be so bad that your uncertainty estimates are meaningless. So some approximations scale better than others. Most don't scale. Though two that scale well are what was that called? MC dropout, which is the one that they use in that paper, which is probably the most well-known approximation. It basically consists of running dropout on your model, and instead of averaging the activation values at test time, you do multiple stochastic forward passes at test time where you zero out some digits, and then the disagreement among the predictions of the different dropout forward passes is taken as the uncertainty estimate. That method is very simple to implement. It doesn't work, it works well, but it's not the best. It has some theoretical issues which have been more recently discovered. Another method that's very recent that works quite well is depth uncertainty, which is from a paper by James Allingham and myself. And the paper's titled Depth Uncertainty in Neural Networks, and it leverages the fact that neural networks sort of provide different representations of the data at different depths, and we can use the disagreement among the predictions from those representations to gain uncertainty estimates. And you can do this in a single forward pass. So that's sort of an advantage that it has over dropout. You don't need to evaluate your model multiple times in order to get uncertainty estimates. Another question is, could counterfactuals, the chat scrolled, 1 second. It's not trivial for me to scroll up in the chat. Okay. Could counterfactuals be used to understand the effect of missing data and maybe optimal replacement? Missing data. So I have a, are you referring to missing data as in missing features, or missing data as in sparse data, as in there's a region of the training data where there is no data, where you haven't sampled? So to address the latter scenario, where there's just simply sparse regions, then counterfactuals can be used for this. Specifically, what you could do is look at these, you could generate these delta clues. Well, actually, I think the best example is this second experiment we do here, where we sort of artificially trigger this scenario, because we create sparsity in regions of the data space by modifying the train set such that these 7s with the horizontal line are missing and the 4s with the triangular top are missing. So we create artificial sparsity, and we show that counterfactuals indeed allow users to identify these failure modes, identify that there was sparsity in the training data. So I think that can be useful for missing data like that. If what you're referring to is having a feature, so maybe you've observed most of the dimensions of the input, but you're missing one, so you haven't queried one specific feature, then I would need to think about that. So usually what's done, so you can do some probabilistic techniques to replace this feature that's missing, such that your prediction will not be altered. But generally what would happen there is that you would choose like the most typical of missing values, such that the prediction that would have been made by the values that you have observed don't change. So this is kind of like saying I choose the less uncertain of the possible values. Perhaps something that you could consider is, are there any, okay, so going back for a second, the reason why you do this, the reason why you choose a very typical value is because you don't want to take your data point out of distribution with your inputted feature value, because then you would have model uncertainty. So there's a clear relationship between data imputation and model uncertainty, because you sort of impute features in order to minimize model uncertainty. Right now, I'm kind of drawing a blank on relating this to counterfactuals, but the relationship might be there. I'm sorry I can't give you a more solid answer. Dropout and ensemble. Okay, so this is, I think this comment about dropout and ensemble is relating to the previous thing about getting uncertainty estimates for image tasks. So dropout is a method which I discussed. Something that I should have discussed that is nice that you brought up in the chat is ensembling. Ensembling is simply the idea that I train 10 different ensembling is the idea from this slide, actually. Let's see if I can pull it up. No, it's this one. It's that I train 3 different models, and because their predictions disagree, the disagreement in the prediction is an uncertainty estimate. Ensembling right now, and for a couple of years it's been like this, is bar none the best method for uncertainty. But it's the most expensive also, bar none, because you have to train multiple neural networks and evaluate multiple neural networks. So there's this trade-off. With dropout, you train one, but then you evaluate multiple. So you only lose at test time compute. With this depth uncertainty approach that I mentioned, you train one and you evaluate one and you get uncertainty estimates. And in practice, those are better than dropout, but worse than ensemble. Ensemble is pretty unbeatable right now in terms of quality of uncertainty estimates. But in practice, I know some people working on self-driving cars, and the reason why they don't deploy ensemble is because you need a frame rate in order to get your car to make decisions quick enough to be safe. And running an ensemble would reduce, you're not packing some crazy GPUs in this car, so you don't have that much compute. And running an ensemble would decrease your frame rate too much. So the safety that you get from uncertainty, you're losing in reaction time. So there's clearly a compute versus quality of uncertainty trade-off. Can you speak a little more about determining in out of distribution data in CLUE? Right. Okay, this is a good question. So I haven't really touched on this. This is perhaps elaborated a little bit more in the paper. Right, so how I've sort of explained CLUE, your model is uncertain about an input and you ask, why are you uncertain? And CLUE says, look, if the input would have been this, then I would not have been uncertain. And I sort of was referring to general uncertainty. And I wasn't specifically talking about if your model is uncertain because the input is out of distribution, or if your model is uncertain because there's noise. But you can, it's very simple calculation to do to separate these two uncertainties. So you can separately measure if your model doesn't know because it thinks there's noise, and if your model doesn't know because it thinks there's, because the input is out of distribution, there's model uncertainty. And what you could do is run CLUE with respect to one of these two things individually. So you could just say, give me an explanation, give me a counterfactual for out of distribution. So if my model thinks that the data is out of distribution, map it back into distribution. And then you would get a CLUE that's only solving for that. Or you could just run CLUE with respect to the noise uncertainty, if your noise uncertainty is high. So then your model would be saying, I don't know, because there's evidence for multiple classes, or I'm in a region where it's impossible to separate the classes. And then you would be asking your model, where would you need to go in order to have class separability? Where would you need to go in order to not have conflicting evidence? I don't know if this answers your question. Okay.
All right, any more questions? There are 38 really quiet people.
By the way, the person that asked about Bayesian neural networks for computer vision, if you're interested in, I have implementations for those in this, I have implementations for both dropout and ensembles in this GitHub repo here, and also some other methods that you might not be interested because they don't scale very well. And that other method, which I mentioned, depth uncertainty, the code is not in this repo, but is also public. And you can find that one on the Cambridge Machine Learning Group's repository, which is now in the chat. Thank you, Wang.
And is there implementation of CLUE that people can try out?
No, well, we're going to publish it when the paper comes out. There's a preprint out, but it's not conference yet. But yeah, CLUE is, if you want to implement CLUE, it's not very difficult, because once you have a Bayesian neural network and a variational autoencoder, which you train on the data, then you sort of just run gradients through these two models. There's a lot of moving parts. So getting everything to play nice with each other in terms of implementation is, you have to sort of fiddle with like your gradients, make sure everything is looking good. But conceptually, it's very simple. There's no hidden tricks. Is there a reference for the method you described to differentiate noise versus model uncertainty? Reference. Yes, there is. Okay, so I don't want to give you a PhD thesis. I'm thinking what the name of the paper is that decomposes it.
I'm finding it. The CLUE paper has it in the appendix. The CLUE paper has it in the appendix. Appendix B of
our
the CLUE
paper has it, yeah.
Yeah, our paper has it in the appendix. If you look at the appendix of the paper Alyssa sent out, it's there, but it's also in Yaron Gall's thesis, which is probably what he was referring to.
Yeah, okay, yes. So you can probably just look at our paper. I'll tell you specifically. The paper's called Getting a CLUE, a method for explaining uncertainty estimates. And it's loading. I'll tell you a second which appendix it's in.
It's in appendix B.
There you go.
And this is Yaron's thesis. And his entire thesis introduces this idea of breaking these two terms apart and studying and proposing dropout and whatnot.
Yeah,
But,
I don't think Yaron's thesis sort of invented these ideas. These are quite
Yeah.
old ideas, but
Sure.
he's definitely very responsible for popularizing them.
Yeah.
Before him, nobody was talking about this, and now everybody's talking about this.
Well, in the machine learning community, the statistics community also calls this like direct versus indirect effect. Just one of the things that Javier mentioned, it doesn't necessarily even have to be a BNN as well, to the auxiliary classifier. It just needs to have, it just needs to be differentiable and have differentiable uncertainty estimates. And
to run clue, that is.
To run clue, yeah. So you don't need a Bayesian neural net. So you can actually try to do this on other models, and we have some experiments on that in the paper as well.
Right, that's a pretty good point. So specifically, like we mentioned, there's two types of uncertainty: noise and model. And you do need a Bayesian model to capture model uncertainty. But if you have a regular model that captures noise uncertainty, just tells you about class overlap, you could still run clue, and it would tell you, it would sort of explain away that noise uncertainty. There is a caveat to this. Because of the lack of model uncertainty, there's some interplay between the two, so that if you don't have model uncertainty, it's very likely that you will underestimate noise uncertainty. So then this is part of the reason why neural networks are very overconfident, because in order to maximize their objective function, what they sort of do is say, I reach a good solution, and then I become arbitrarily confident. I become super, super confident on this solution that I've reached, because then I'm able to explain all the training points perfectly. So in order to minimize my loss, I just make like 100% confidence on those training points. And this results in very confident, predictions on test points. But when you have a model uncertainty, that prevents this delting, that prevents this closing in of the noise uncertainty. So you end up having a better estimation of both types of uncertainty once you include model uncertainty in there.